Hi there, in the previous video I went through the method in order to investigate whether your two lines are either intersecting, parallel or skew. So I went through the method in the previous video and I broke the method down into steps. Now in this video I'm going to try some examples of how to apply this method. So let's try some examples. Hope you can see that. So example number one. So let's take this red pen, underline. So in the first example, let's prove that. So prove that the lines. So the first line is r that is equal to 2i minus j plus k plus lambda into I minus 2j plus 2k, and we have another line, have an equation r equals I minus 3j plus 4k plus mu, open a bracket, 2i plus 3j minus 6k, and we need to prove in this case that the lines are skew. So remember in the previous video, skew means they're not parallel, they're not intersecting lines. Okay, so skew, remember, not parallel, not intersecting. So remember the steps involved. Now step number one is to prove that these lines are not parallel. So remember, skew means they're not parallel, not intersecting. In step number one, to prove that they're not parallel, remember in the previous video, look at your direction vectors, and if one of the direction vectors is a scalar of the other, that implies that they're parallel. However, if one of the direction vectors is not a scalar of the other, that implies that they're not parallel. Okay, so that is step number one. So back to this example. So if I take a red pen, here are my direction vectors. So as you can see, I can't make one of them a scalar of the other, so that implies that they're not parallel. Okay, so since I minus 2j plus 2k is not equal to a scalar which I'm taking as t into 2i plus 3j minus 6k. Okay, that means that, so therefore, so if I call one of the lines L1, the other line L2, so that implies that L1 is not parallel to L2. Okay? So we've proved that these lines are not parallel, so that is one of the requirements of skew. So remember, skew means not parallel but not intersecting. So let's prove that they're not intersecting. So remember, in the previous video, step number two is equate the given vector equations of the line. Okay, so equate the vector equations of your lines. Okay, so that is step number two. So let's do that over here. So the first line, L1, so that is 2i minus j plus k. Okay, and plus lambda into I minus 2j plus 2k, and that is equal to L2, which is I minus 3j plus 4k plus, let me expand this out, makes it a little easier, so plus mu into 2i plus 3j minus 6k. So plus 3j minus 6k. Okay, so that is step number 2. So let's remind ourselves of step number 3. So in the previous video, step number 3, remember, is to group the I, j and k components on both sides. So we're going to group the I, j and k components in this example. So let's do that. So group I, j and k components on both sides. So looking at the I components, so starting with the left hand side, I have 2 plus a lambda times 1, so 2 plus lambda with I, plus if I group the j components, so I have minus 1 and a minus 2 lambda, so minus 2 lambda with j outside, plus if I group the k components on the left, I have 1 plus 2 lambda k, and that is equal to, if we do the same, so if we do the same on the right hand side, so in this case I have 1 plus 2 mu with I, so 1 plus 2 mu with I, plus grouping the j components, minus 3 plus 3 mu, so minus 3 plus 3 mu with j, plus grouping the k components, 4 minus 6 mu, so 4 minus 6 mu into k. Okay, so that is step number 3. Group the I, j, k components on both sides. So remember in the previous video, the next step, step 4, is equate the coefficients of I, j and k on both sides to come up with 3 equations. Okay, so let's do that in this case. So in this example, let's equate coefficients of I, j and k on both sides. So if we equate the coefficients of the I unit vectors on both sides, so if I take a red pen, coefficient of I on the left is 2 plus lambda. That's equal to, on the right hand side, the coefficient of I, 1 plus 2 mu. So 2 plus lambda is equal to 1 plus 2 mu. Let's call that equation 1. Okay. If I do the same with the j unit vectors, so coefficient of j, taking a green pen, left hand side, minus 1 minus 2 lambda. So minus 1 minus 2 lambda. That is equal to, on the right hand side, coefficient of j is minus 3 plus 3 mu. So minus 3 plus 3 mu, let's call that equation 2. Okay, and if I do the same with the k coefficients, coefficient on the left is 1 plus 2 lambda, so I've outlined it in black, and on the right, coefficient of k, underlined in black pen, is 4 minus 6 mu. Let's call that equation 3. Okay, so here are the 3 equations that we have in step 4. Now, if we go back, remember step number 5, take any 2 equations and solve simultaneously to find lambda and mu. So you just take any 2 equations and use only those 2 equations to find lambda and mu. Okay, so let's have a go over here. So step number 5. Okay, so in this case, let's take 2 equations. So looking at my 2 equations, that I have. Okay, so if I take, for example, equations 2 and 3, okay, so I'm taking 2 and 3 purely because if I add them, my lambdas will cancel each other out. So I'm going to take 2 and 3 and use only 2 and 3 to work out lambda and mu. Okay, so in this case, using equations 2 and 3, okay, so in this case equation 2 is -1 minus 2 lambda, that is -3 plus 3 mu. Equation 3 is 1 plus 2 lambda, that is 4 minus 6 mu. And as I said, if we add them, the lambdas and the minus ones also will cancel, giving us 0, that is equal to 1 minus 3 mu. That means mu, when I rearrange, is 1 over 3. Okay? And if I replace the mu in one of these equations, I can find lambda. Okay? So if I put mu is equal to 1 over 3 into, so let me put it into equation 2, for example. So into equation number 2, we're going to have -1 minus 2 lambda, okay, that is equal to -3, okay, plus 3 into mu, which is 1 over 3. So these two 3's you can cancel, okay, so you're going to have 1 minus 2 lambda, that is equal to -3 plus 1 is -2. Now if you simplify, you'll eventually get to this stage. -2 lambda is equal to -1, which when you rearrange, lambda will then be half. Okay, so in this case our mu value is 1 over 3, our lambda value is half. So remember the next stage. The next stage is we need to put the mu and the lambda values into the equation we haven't used. So let me just remind you. So that was step number 6. You put the lambda and mu values into the equation which was not used, okay, in step 5, the previous step. So I used equations 2 and 3, so I need to put these values for lambda and mu therefore into equation number 1. Okay, so there's equation number 1. Okay, so let's do that. So here is step number 6. Put lambda is equal to half and mu is equal to 1 over 3 into equation number 1. Okay, so equation 1 is 2 plus lambda, that is 1 plus 2 into mu. So if I replace the values, lambda is half. On the right hand side we have 1 plus 2, mu is a third. Okay, so as you can see over here, 2 plus half, that is 5 over 2, and that is definitely not equal to 1 plus 2 of 1 over 3, which is 5 over 3. Okay, so the left does not equal the right hand side, so hence we have skew lines. So since left hand side does not equate to, okay, the right hand side, so therefore we indeed have skew lines. Okay, so that is what we need to show anyway in the question, so we've proved that using this method. Okay, so that completes that example. Right, I think another example is in order, so let's try another one. So let's call this example 2. Take a pen. So in example number 2, so let's find whether the following pair of lines are either parallel, intersecting, or skew. Okay, so the first line is L1, and that is defined by x minus 4 over 1, which is equal to y minus 8 over 2, which is equal to z minus 3 over 1. So this line is in Cartesian form, remember. And the second line, L2, that is defined by x minus 7 over 6, which is equal to y minus 6 over 4, which is equal to z minus 5 over 5. So we need to determine whether these lines are either parallel, intersecting, or skew lines. Okay, so let's go through the method. So in step number 1, we need to show whether they're parallel or not. Okay, so remember, we need to look at the direction vectors of both of these lines. So let's work out firstly the direction vector of the first line L1. So direction vector of L1. Now remember, in one of the previous videos where I explained the relationship between vector, parametric and Cartesian forms for the equation of the line. So in that video I explained that the terms in the denominator of your Cartesian equation, these are the components of the direction vector of the line. So the terms 1, 2 and 1, these are the components of the direction vector of L1. So in this case I could write that as 1i, okay, plus 2j plus 1k. Okay, so I wrote that in vector form. Okay, and let me do the same with L2. So the direction vector of L2. So once again, the terms in the denominator, these are the components of the direction vector when looking at the Cartesian equation. So 6, 4 and 5 would be 6i plus 4j plus 5k. So that's the direction vector of L2. Okay. Now you don't need to do this. You can actually look at these components to find out whether they're parallel or not. So remember the condition for parallel: if one of the direction vectors is equal to a scalar multiple of the other, that means that the lines are parallel. Okay, but in this case, if I take one of them, one of these direction vectors cannot be written as a scalar of the other. So in this case, since I plus 2j plus k is not equal to, so that does not equal to a scalar, which I normally take as t, into 6i plus 4j plus 5k. Okay, so in this case, therefore L1 is not parallel to L2. Okay, so these two lines are not parallel. So let's go to step number 2. So in step number 2, so let's have a look at step number 2. So step number 2 is we need to equate L1 to L2. So we need to equate the vector equation of the first line to the vector equation of the second line. Okay. So I found the direction vectors of the lines. Okay. And remember, in the previous video, when I explained the relationship between vector, parametric and Cartesian equations of a line, not only I mentioned about how the denominators of your Cartesian equation are related to the direction vector, okay, I also explained rather that provided that you have negatives here in the numerator, so provided that all of these are negatives in the numerator, these terms, so the terms 4, 8 and 3, these are the components of the fixed point vector of your line, okay? So in this case, the fixed point vector of the first line L1, okay, would be 4i plus 8j plus 3k, and the fixed point vector for L2 is 7i plus 6j plus 5k, okay? So with that in mind, okay, in vector form, the equation of L1 is 4i plus 8j plus 3k, so that's the fixed point vector, plus lambda into the direction vector of L1, we wrote that earlier, that is I plus 2j plus k, and we're going to equate that to, so let me just open this up, so we're going to equate that to the line L2, so the fixed point vector of L2 is 7i plus 6j plus 5k plus mu into the direction vector of L2 written earlier, that is 6i plus 4j plus 5k. Okay, so that is step number 2. So remember the next step is, so let's go back to the method. Step number 3 is to group the I, j and k components on both sides. So let's group them in this example. So step number 3, group I, so all of these should have arrows, so I missed the arrows. So all of these unit vectors I, j and k should have arrows. So let me quickly include them. Right, so group the I, j and k components on both sides. So on the left hand side, let's group them. So I've got 2 components, so I have a 4 plus lambda, so 4 plus lambda into I, plus if I group these 2 j components, I have 8 plus 2 lambda, so 8 plus 2 lambda into j, plus if I group the k components, I have 3 plus lambda into k, and that's equal to, let's do the same on the right hand side. So if I group the I components, I have 7 rather, so 7 plus 6 mu into I, so 7 plus 6 mu into I, plus if I group the j components, 6 plus 4 mu into j, so 6 plus 4 mu into j, plus, and finally with the k components, 5 plus 5 mu into k, so 5 plus 5 mu into k. Okay, so that was step number 3, grouping the components on both sides. And if you remember in the methods, the next step number 4, is to equate the coefficients of I, j and k on both sides in order to create 3 equations. Okay, so let's do that in this example. So let me continue over here. So step number 4, equate coefficients of I, j and k on both sides. So if I equate the coefficients of I, so let's do that. So if we go back the coefficient of I, if you could see, on the left hand side is 4 plus lambda. So let me underline that in red. Okay, that is equal to the coefficient of I on the right hand side, which is 7 plus 6 mu. Okay, so let's include that over here. So 4 plus lambda is equal to 7 plus 6 mu. Let's call that equation 1. So if I do the same with the j components, so on the left I've got 8 plus 2 lambda, and on the right I have 6 plus 4 mu. Okay, so let's take a green pen. So on the left hand side 8 plus 2 lambda, and on the right hand side 6 plus 4 mu. So 8 plus 2 lambda, that's equal to 6 plus 4 mu. Let's call that equation 2. And let's create another equation. So if I equate the k components, I've got 3 plus lambda on the left hand side. That is equal to 5 plus 5 mu on the right hand side. So in this case, 3 plus lambda, that is equal to 5 plus 5 mu. That's equation 3. Okay, so here are the 3 equations that we have. So in the next step, step number 5, so let's remind ourselves, step number 5 is we take any 2 equations and solve simultaneously to find lambda and mu. Okay, so looking at this example, if I take equations 1 and 3, and if I subtract, I can get rid of lambda. Okay, so that's what I'm going to do. So I'm going to take equations 1 and 3 and solve simultaneously to find lambda and mu. So if I take 1 and 3, so let's tick them. So 1 is 4 plus lambda, that's 7 plus 6 mu. 3 is 3 plus lambda, that is 5 plus 5 mu. So if I subtract them, okay, the lambdas will be eliminated. 4 minus 3 is 1 on the left, 7 minus 5, 2, plus 6 mu minus 5 mu is mu. So when I rearrange, mu minus 1. Okay, so that's the value of mu. So let me substitute that value into, let's say, equation number 1, say, yeah? So let's put that value into equation number 1. So here's number 1. I'll have 4 plus lambda, that is 7 plus 6 into minus 1. When I do the replacement, 4 plus lambda, therefore 7 minus 6 is 1. Lambda, when I rearrange, 3. So that should be the value of lambda. Okay. So that is step number 5. And step number 6 is, so if we remind ourselves, so let's go back to the method. Step number 6 is to put the lambda and mu values into the equation which was not used and check whether the left is equal to the right or whether the left is not equal to the right. Remember, if left equates to right, it's intersecting lines. Left hand side does not equate to the right hand side, implies skew lines. So let's go through that step. So step number 6, so let's put mu is minus 1 and lambda minus 3 into, and the equation that we haven't used is number 2. Okay, so here's equation number 2. 8 plus 2 lambda is equal to 6 plus 4 mu. So when I do the replacement, I'll have 8 plus 2, lambda's minus 3. On the right, 6 plus 4, mu is minus 1. And clearly, they do equate to each other. So 8 minus 2 of minus 3, okay, is 2. That is equal to 6 minus the 4, 2 also. So since the left is equal to the right hand side, we have intersecting lines. So since left hand side is equal to the right hand side, therefore L1 and L2 intersect. Okay, so we've shown that these two lines are intersecting, but remember I made a note in the previous video, so if they're intersecting lines, to find the position vector of the point of intersection, you can put either lambda or mu into the lines L1 or L2. So it doesn't matter, you're going to get one point of intersection. Okay, so you can either put lambda into the first line or mu into the second line. You're going to get the same answer because you only have one point of intersection. Okay, so let's do that. So I'm going to use my lambda value. So if I put lambda as -3 into, so looking at L1, so let's do that. So L1, so I'm going to use this form. Okay, so this is our L1 in vector form. So we're going to have 4i plus 8j plus 3k plus the lambda is -3 into I plus 2j plus k. So let's have arrows on these unit vectors I, j and k. Okay, so I've put my lambda value, which is -3, into the vector form, which I've written over here. So the left hand side is the equation of L1 in vector form, the right hand side is the equation of L2 in vector form. Okay, and if you add the like components, so if you add the I, j and k components, you should have I plus 2j. Okay, so that is the position vector of the point of intersection. If you want to write that as a coordinate, in coordinate form, the coefficients of I, j and k will be the values of x, y and z respectively. So as a coordinate, that would be 1, 2 and 0, as you've got 0 k component. Okay, so 0 is the z value. So that completes that example. I hope you found this video helpful, and I hope to see you in the next video. Thank you.